Welcome! In this video, I'm going to discuss all about the Fourier series of bipolar rectangular wave. I am going to show its derived solution of exponential form, combined trigonometric form, and trigonometric form to get its result rectangular waveform. Furthermore, I will be discussing the computation of the BRMS, the waveform of different transformation of signals, the simulated circuit, and the actual simulated of the circuit. Using the rectangular waveform shown in the figure, we will first represent this into a mathematical expression. We can write it mathematically as x of 1 of t is equal to v of 0 less than t and dt over 2 greater than t, minus v of dt over 2 less than t and t times 1 minus d over 2 is greater than t, and v of t times 1 minus d over 2 less than t and t greater than t. So for us to get the exponential form, we'll first find the ck or the coefficient. So ck is equals to 1 over t times the integral of 0 to t xt times e raised to negative j k w sub naught times t dt. So upon substituting the value of xt, we arrive at ck is equals to 1 over t times the integration of 0 to dt over 2 times v times e raised to negative j k w naught times t dt minus the integration of dt over 2 and t times 1 minus d over 2 v times e raised to negative j k w naught times t dt plus the integration of t times 1 minus d over 2 to t v times e raised to negative j k w naught times t dt. So, we will first substitute the value of the w naught. W naught is equals to 2 pi over t. So, upon substituting, ck is equals to v over negative jk times 2 pi over t times t, and so on. And upon the integration and computing the coefficient or the ck, we arrive at the answer of ck is equals to 2 times vd times sine k pi d over k pi d. Next is the computation of the c sub 0 or the c0. C sub 0 is equals to 1 over 2 times t times the integration of 0 to t xt dt. So upon substituting the value of x of t, c sub 0 is now 1 over 2 times t times the integration of 0 to dt over 2 v dt minus the integration of dt over 2 to t times 1 minus d over 2 v dt plus the integration of t times 1 minus d over 2 to t v dt. So, upon integration, c sub 0 is equals to v over 2t times dt over 2 minus 0 minus t times 1 minus d over 2 minus dt over 2 plus t minus t times 1 minus d over 2. C sub 0 is equals to v over 2 times t times dt over 2 minus t plus dt over 2 plus dt over 2 plus t minus t plus dt over 2. And now, c sub 0 is equals to v over 2t times 4 dt over 2 minus t. And upon computing, the result now is the c sub 0 is equals to v over 2 times 2 times d minus 1. So, for the computation of the VRMS, the formula of VRMS is equals to the square root of 1 over t times the integration of 0 to t x t raised to squared raised to 2 dt. So upon substituting the formula of xt, VRMS is now equal to the square root of 1 over t times dt ay 0 into the integration of 0 to dt over 2 v dt minus the integration of dt over 2 t times 1 minus d over 2 v dt plus the integration of t times 1 minus d over 2 to t v dt and squared. VRMS is equals to the square root of b squared over t times dt over 2 minus 0 squared minus t times 1 minus d over 2 minus dt over 2 squared plus t minus t times 1 minus d over 2 squared. So, upon simplifying and computing the VRMS, we arrive at the answer of VRMS is equal to 0.592. So, for the form of the bipolar rectangular wave, or the Fourier series of the bipolar rectangular wave, we will use the frequency of 1, t of 1 over f, b is equals to 1, w is equal to 2 pi over t, the distance is equal to 0.5, the j is equals to the square root of negative 1, and the time is 0.0 and 0.0001 2t. So, for the exponential form, we, we will use the formula for exponential form, and we will substitute the coefficients, and it arrives like this. And the waveform of the exponential form, or the results of the derivation of the coefficient, and upon substituting, the exponential form of the rectangular wave is now like this. For the trigonometric Fourier series, so we'll first compute the trigonometric Fourier series. So the given is CK is equals to EK plus I times VK over 2. So CK, AK, and VK is the coefficients of the Fourier series. AK is equals to 2 times CK. So since rectangular wave is an even function, Vn or Vk is equal to 0. So for the CK, we have 2V times this sine C k pi d. So since AK is equals to 2 times CK, we'll substitute the value of the CK. So now the AK is equals to 4B times D sin k pi d. And we have the result for the C naught, which C naught is equals to V over 2 times 2D minus 1. Since C naught is equal to A naught, so so A naught is equals to V over 2 times 2D minus 1. So this is the formula for the trigonometric Fourier series. X of t is equals to A naught plus AK times cos k omega W sub naught times t. So upon substituting, we have now the trigonometric form, and it is just like the same as the exponential form. And for the combined trigonometric Fourier series, CK is equals to 2V times this sine CK pi d. So C naught is equals to A naught. A naught is equals to V over 2 times 2D minus 1. So theta K is equals to negative arctan VK over EK. Theta K is equals to negative arctan. So since it is rectangular, so VK is equals to 0. So now theta K is equals to 0. So upon substituting the given answer, or the given, we arrive at this kind of waveform in combined trigonometric form, and it's just like the exponential form and trigonometric form. So for the VRMS equals to the square root of t times v squared minus 1 plus d is over the square root of 2 is equals to 0.5. So for the transformation of signal, here is the transformation of the signal. It is the transformation signal of the time reversal, the time scaling, the time shifting, the amplitude reversal, amplitude scaling, and amplitude shifting. So these show the bipolar rectangular wave or the simulation of the bipolar rectangular wave. As the result of the oscilloscope, it is now a rectangular waveform using this circuit. I use this circuit for the actual simulation of the bipolar rectangular waveform. Shown is the actual simulation of the bipolar rectangular waveform and its results in actual. That would be all. Thank you.